All right, hello folks. We're gonna do another Gen AI book club session today, and today we're gonna cover a topic that a lot of people had requested um, a couple months ago, which was how to fine tune their own models. Since we started this book club and now, a lot has happened in the space that has made this much more possible and much easier than it was just a couple months ago. So just off the top of my head, there's a couple new tuning services that are available and really easy to use. We're going to go through one of them, which is AI Studio in at Google. And then also, there's been a number of small model releases. So we'll get into this in a second, but with bigger models, they're more challenging to fine tune because you need more compute resources. But now we have a Mistral 7B model, we have a Gemma 7 billion and 2 billion parameter models, and that makes it easier, so not completely straightforward, but easier to tune models locally. So I'm going to do something brave. I'm going to try and go through all these things live with you. If you want to watch the recorded edited video, it's available on the Gen AI Book Club in the middle. So that'll get you the fine tuning for AI Studio. But we're going to try and do it all together. So let's just go ahead and jump straight into it. If you're around, let me know, because I'm always curious who is watching and what they're into. But in the meantime, let me just give you the intros. All right. So if you're not familiar with fine tuning, there is this chapter or this guide in the guidebook that talks about tuning in general. Ooh. And I'm seeing an error on YouTube. So if anybody's on YouTube and they are not seeing this video, I guess let me know. I might have to say this. All right. Nitesh, always, I'm so excited to present to you. All right. So if you don't know what fine tuning is, I won't cover that today. There is this entire guide that we've gone through before, but the short and the long of it is that you have a model, either a pre-trained model or an instruction tuned model, and you just want it to act differently in some sort of way. Maybe you want the answers to be more verbose. Maybe you want the answers to be in a certain style. What you do is you do this process called fine tuning. You essentially train the model, you fine tune it to behave in a different sort of way. There is a number of different methodologies for fine tuning that are used. We're going to be going through one of them, which is supervised fine tuning, which you'll see today, where we provide the prompt and the response, which I'll talk about in a minute here. But this is becoming very common. Just in the AI space, you get these large, or you get these foundation models or models from companies like Google or OpenAI or Cohere or Mistral, and they work in a default way. But now you, as an individual or as a company, want things to be different. You want your model to respond differently. You want it to say maybe yes to certain questions and no to other questions that it wasn't trained to do so before, and you use fine tuning to do that. So let's talk about what we want our model to do. What we want to do, if I go to this section, is we want our models to output recipes, but we want them to output them with JSON and in a Shakespearean style. So this is a little bit weird. I mean, usually when people ask for recipes from a ChatGPT or Gemini models or any other model, they typically don't want a format like this, right? They want a nice textual format that gives them the recipe for apple pie, but that's not what we want. We want this. So let's go, for instance, we'll go to Gemini and we'll say, I want a recipe for apple pie. And we get this. Pretty standard, looks quite nice. But it's not exactly what we're looking for. We want to change this model's behavior to provide us to provide us an answer that looks and is in Shakespearean and is in JSON. This is neither. This is just plain text, and this feels like it's written in a modern language. So what we're gonna do is we're gonna do one thing first, and then I'll show you a couple ways. I'm going to talk through how to create distillation examples from larger models so you can see what that process looks like. I'll then show you tuning in AI Studio, which should be straightforward and should just work. And then I'm going to attempt to show you local tuning on a desktop. This is probably going to run a little bit longer as a session. Maybe I'm going to estimate till about for another hour, an hour and 10 minutes. But hopefully then it'll give you a good hands-on just consolidated video of how these different things work. All right. So the first thing we need to do is we need to generate a bunch of fine-tuning examples like this. So we need a bunch of prompts, and then we need a bunch of outputs. This is called supervised fine-tuning, or these are examples that we need for supervised fine-tuning, and it's one of the ways in which we can shift a model. We can, it's one of the ingredients, if I use the word here, that you need to fine-tune or shift a model's behavior if you're going to use supervised fine-tuning. So the way I did this, and I'll post the link in here in the appendix, all the code that you're going to see is available in the appendix of the book. You're going to have small model fine-tuning. I should rename this to be model fine-tuning, but nonetheless. You're going to have all the notebooks that we're going to go through. The first notebook we're going to go through is distiller.py or .ipynb. I'll post that in the chat as well for the YouTubers. So what we're going to do is this process called distillation. Distillation is a means where you can take a big model that already has the behavior that we want, and you can get it to provide examples that we can use to train other models. So in this tutorial, you're going to see me use this thing called Ollama a lot. Ollama is this very handy model library and interface that makes it simple to both grab models and also interact with them. In this case, I used Ollama, which you'll see later on. Well, in this case, I'm using Ollama's Python interface to grab Gemma 7b, which is a Google open source model. And I'm asking it for 20 foods with less than 3 ingredients per recipe in a bullet form. And it does a pretty good job of giving that to me. I want simple recipes so they're easy to see and don't create a lot of JSON that becomes hard to scroll through. And I need 20 of them. So here we go. I get a pretty nice standard list. I just copied the list again into Python hard-coded, so it's easy for people to reference and they can use it later. But here we go. We have 20 recipes. Now what I'm going to do is I'm going to ask a bunch of models to provide me recipes for the food with instructions written in a Shakespearean style in a JSON format. Why am I doing this? I need 20 examples, but I don't want to write these examples out by hand because the other mentality and constraint that we're taking in this entire exercise is we're going to be doing this as individuals who don't have hundreds of thousands or millions of dollars and don't have a lot of time in a whole research group. This is specifically a guide for folks that are fine-tuning on their own. If anybody's curious about fine-tuning at enterprise scale, just let me know. I can go through the guidebook again later. But we're going to be doing this like we are individuals that don't have a lot of time and money, which is, I'll say enterprise level, let's say Meta level or Google level or OpenAI level investment in our fine-tuning setups. So because of that, we don't want to spend a ton of time writing our own prompts. We're just going to ask models that have already been trained to generate a bunch of prompt response pairs for us. So here you can see Llama 70B, a fairly large model. The biggest, actually it's not the biggest open weights model anymore. The Databricks just released an even bigger open weights model, but it was I think it's now the second biggest open weights model, or one of the bigger ones. We ask it to give us JSON Shakespearean recipes, and here you have it. It's doing it. So it's giving us a pretty okay example, name, instructions in a JSON format. It gives us all this other stuff at the end, which I don't really want, but nonetheless, it does it. Next, we're going to ask Gemma, which is Google's open source 7 billion parameter model. Also, there's a 2 billion parameter variant, but the 7 billion parameter is what we have here. Looking at it, I actually like this format a lot. It gives the JSON marker, and then it gives us the JSON in the middle with no extra text. Likewise, we go to Mistral. Mistral actually does a pretty good job, right? It gives us this name. It looks pretty Shakespearean. It gives us a longer JSON. And so looking through these three, the model that I like the best is Gemma 7B. So if you're going to be doing distillation, my first piece of advice to you is just try a bunch of different models out, tweak the prompt and tweak the different models, and see which works for you. I happen to like Gemma the best. So now that I know that, I'm going to go ahead and I'm just going to go and ask every single model for 20 examples each for each one of the ingredients. So in this loop, we're going through every model. We're giving it the JSON prompt. We're capturing the response. We're then doing one more thing, which is rewriting the prompt. So I want you to just look at this for a second. I'll come back to it. But we're then capturing the ID of the example, the food, the rewrite prompt, and the completion. What we get in the end is we get a bunch of JSON long examples. They're all stored on disk. And now I have all my supervised fine-tuning examples. All right. So this is the first step. We haven't actually gotten to fine-tuning yet. We're just doing what's called distillation. If you have any questions about distillation, go ahead and ask them now, because I'm going to go and I'm going to pull up the distillation examples in Google Sheets and show you how we're going to use these in AI Studio to train the model. So I'm conveniently also going to leave this up while I pull up some Google Sheets. So this is a good time to, again, ask any questions if you have them. Go to Sheets. All right, I'm not seeing any. So here's what you're going to see next. Let's see if I have access. Yes, I do. All right, so I've taken those JSON examples and I've just put them into a Google Sheet, which you'll see why in a moment. We have a couple of things. We have the food, we have the prompt, we have the rewrite prompt, and we have the completion. All right, Nitesh asks a question, which I'll address immediately. Do we typically use smaller models to generate distillation examples? That's an excellent question. I'm going to show you exactly in the book where I explain this. So, I think I wrote in the book. Let's find it. All right. So I'll verbalize the answer here. I'll speak it out loud, but I'll also show you that it's in the book. Generally, when doing distillation, the idea is you use a larger, more capable model, which can do much more. Like let's say a GPT-4, and you use it to fine-tune any other model. Let's say you're going to use it to fine-tune a Mistral 7B. That's what most people think of when they're talking about distillation. Large, super capable model has tons of ability to answer all sorts of different prompts, and you use that to make smaller models better. But it doesn't always have to be the case. Before I go on to explain why, typically the idea is that large models can do everything. The cost, though, is they're hard to fine-tune because they're super large. Sometimes you can't fine-tune them. I actually don't know if you can fine-tune GPT-4 right now. The second is they're expensive to run. So you have this GPT-4 model that can do everything, but you really just needed to do like one or two things, not the thousands of things that LLMs can do. So you train that behavior that GPT-4 can do on those one or two examples into a smaller model, and then that smaller model is much easier and faster to run. As a quick example, just to talk about that, when I was running Llama 70B, it took about 40 minutes to run the 7B distillation, and it took about 3 minutes to run the Gemma and Mistral 7B distillations each. For reference, I'm using a, if I show you where that is. So this, to word that again, this running these 20 examples took about 3 minutes. This took about 3 minutes. And then this took about 40 minutes. I'm using a NVIDIA RTX 4090, by the way. So it's a fairly substantial consumer GPU. So to answer your question very directly, did we generally use smaller models? Actually, generally people use larger models, and then they use those to fine-tune smaller models. But in this case, I actually prefer the example. I prefer this response from Gemma 7B quite a bit. So we're actually going to use a small model to fine-tune a bigger model in the API. So the flip. So I guess the other thing I want to tell you with AI right now, there's not a lot of rules. People are figuring this out. So if you have an idea and you think you want to try it, I would just tell you to go try it. So just because you see people fine-tuning bigger models or distilling bigger models to fine-tune small models doesn't mean you can't go the other way around as well. All right, excellent question though. That's one that comes up quite often. All right. So to touch this point, we're going to now use a small model. These are the Gemma 7B examples. And we're going to use these to fine-tune a big model, which is Gemini Pro. We're going to do Gemini 1.0 Pro. So you saw, oh, this was the Gemini 1.5 example. So let's go ahead and let's reprompt. Let's do this again using Gemini 1.0. For those who don't know, now Google has a number of models available in AI Studio. There's 1.0 and there's 1.5. 1.5 is pretty big. Actually, they're both big models, but 1.5 is a bigger model. It has a 1 million token context window, which is ridiculous and pretty cool. And we can go into 1 million token context windows at some point. But let's try this again. Let's say I want a recipe for apple pie. Let's see what 1.0 gives us. All right, very similarly worded example, pretty standard recipe. What we want though is we want our model to be fine-tuned and JSON-y. So in very typical cooking tutorials that if you've seen American style cooking tutorials, they jump to the end. I'm gonna show you one that I've already fine-tuned and then we'll go through the process. So I'm gonna go use a freeform prompt on my already fine-tuned model. I'm gonna say, I want a recipe for apple pie. Let's run this. And already you can see that this output is quite different. I'm on AI Studio. This is a model that's not running on my computer. It's running on Google servers. And we're getting a very different response than we were just earlier. It's not super great. Like there's some issues. We'll talk about in a second how to get around this. But the point is, you can see it's already behaving differently. This is actually really cool, right? It's actually, before we get into the details, really neat that you can take a model that's already massive and deployed on another company's servers, and you can change its behavior to be closer to what you want it to be. So let me show you the process. If you have questions about this is a good time to ask because we're going to have a couple minutes wait as we wait for the tuning to happen. So any questions, drop them in the chat. In the next minute or two, I'll show you how to do this. So the UI will show us we want to create a new tune model. It's right here on the left. Click OK. What I'm going to do is create a tune model name. I'm going to say livestream tune model. All right. I'm going to choose a base model. Right now, only 1.0 is available. And I'm going to import in my file. So I'm going to hide this for a second so I don't dox myself. Give me one moment. Okay. So now that we have that, you go in, you find the Google Sheet that you want. I have a lot of Google Sheets that are not relevant to distillation, but this one is. So I'll go in, hit recipe distillation. Now you see that our examples come up. So these are the same ones that we had in the Google Sheet. What we want is we want to grab the rewrite prompt this is the input column, and then we want the completion, which is the output column. The reason we don't want to use the original prompt is we want our model by default to provide Shakespearean JSON examples. So we don't want to say, what is a recipe for apple slices with cinnamon written in a Shakespearean style with JSON. We want the prompt that is just, what is a recipe for apple slices with cinnamon, to automatically give us a Shakespearean JSON example. And so the distillation prompt I use is different than the input prompt I'm going to use for supervised fine tuning. I'm going to go ahead. I'm going to import 20 examples. We can see in the UI here that it confirms our first one is good. If we want to look at other ones, we just can go back to the sheet. If you want, there's some advanced settings. You can go and change things like the tuning epochs, learning rate multiplier, and batch size. Tuning epochs and learning rate multiplier, these will affect the how much the model gets fine-tuned and how fast it does. I won't go into these parameters right now at the moment. I'll talk about them more when we get to the local tuning, because you'll see much more. But for those who've taken a number of the state-space model classes or Bayesian, the neural network examples that we did earlier, you'll recognize these as common parameters that are often used in model training. Anyhow, with everything set up, I'm going to go ahead. I'm going to hit tune. So we'll give it a second. All right, now we see that our model is in queue. I'm going to go ahead and click on it. So here's where we wait. Because what's happening is now our tuning job has been kicked over to Google servers, and Google is putting it into a queue for it to be tuned. I guess there must not a lot of people have been using, I guess a lot of people haven't been using the servers today, because it tuned really fast, actually. Usually, sometimes I've had to wait a little bit longer. But now I can go and I can click C-Tune model. We'll go ahead and use this in a freeform prompt. And I'll say, I'll give it another example. One moment here. Let's go back. All right. Okay, it's already given us the previous example, but I'll say again, I want a recipe for eggs. I'll hit run. And this is a lot closer. Okay, so it's not perfect. There's some issues in that the JSON isn't perfectly formatted. We do get some of it in JSON, like eggs and cheese, and this actually looks like a pretty good, honestly, recipe. I'm pretty hungry, and I want to eat this. And we get our instructions in a Shakespearean format. So what I'm first off happy that the model behavior changed. That's what we were going for. So we have that. But now you see this isn't like the greatest format. We didn't quite get exactly the intended behavior that we're looking for. So things I would do here, one is I would go back and I would check my supervised fine-tuning examples and see if they're correct. If your supervised fine-tuning examples are not good, you're going to run into issues. And here you can already see that they're wrong. This particular distillation run, my examples were bad. And because my examples are bad, my tuning is bad. So my first advice for fine-tuning, always, is make sure your data quality is as high as it possibly can be. The better your data quality is, the smoother the whole thing is going to go. Sometimes it feels like you want to rush to get to the fine-tuning aspect, and you just want to get through the data really quickly. But I promise you, you should spend a lot more time getting good examples and comparatively less time messing around with the actual fine-tuning process itself. The second is we only have 20 examples. That's not too many. I would consider this to be the bare minimum. The reason I chose 20 examples was it made it more tractable and faster to tune, because there's just less to tune on. So it would make these live streams and the guidebook easier to write and for you to read. But in practice, I would shoot for maybe 100 to 1,000 examples. The trade-off then, of course, being is once you have that many examples, then going through and reading them all for quality takes that much longer. So you're just going to have to make a decision between, I would say, getting as many good examples as you can, rather than getting a lot of crappy examples. So I would get as many good examples as you can, rather than shooting for many examples. But 100 would be probably the number that I would go for here if I was serious about this project and something I was deploying to customers. I would get 100, I'd read through them, and then ask my colleagues maybe to read through 100 as well. All right, and so there you have it. That is supervised fine-tuning in AI Studio with Gemini. Very straightforward process, super cool. And then the nice part about AI Studio is you can then grab an API key and you can run this. You can then let me word this again. You can grab an API key and then you can call this model from Python or anywhere you want. So you click Get Code, and here we have the code in Python for our supervised fine-tuning model. You go in, put your API key in, get the generation config has already been set, and then you have your tune model here, and there you have it. Okay, one successful fine-tuning example down. That actually went much more smoothly than I thought it would, which is great. You never know with live demos. It's always a hard thing. So I will have another call for questions here. If you're curious about API model fine-tuning, go ahead and drop those in the chat. What we're going to do next is I'm going to show you how to tune a model locally. We'll tune using Ollama, and then we'll go into an example where I show you how to actually fine-tune a model locally using Hugging Face supervised fine-tuning training. Okay. With that, let us jump straight back into it, and I will see the questions come into chat, but we'll pause and address those as they come. The next thing I'm going to show you is Ollama. So Gemini and Gemini Pro and AI Studio are great. Those models are not running locally though. They're running on Google servers. That's not necessarily a bad thing. The deployed models are huge, and so it is very unlikely that any individual is going to have a data center sized TPU setup at home. So the biggest models like GPT-4 are reserved for data centers, and you need a big company to run them. But these days, there's a growing movement to have models that are locally owned, open weights models that are locally run on your particular desktop. And what we're going to do is we're going to talk through Ollama, which is my favorite model runner of choice. So this isn't fine-tuning yet. This is just going to be me showing you Ollama again. But here we're going to say Ollama run Mistral, and we're going to get a Mistral model. Actually, yes, Mistral. Okay, so I'm going to say, what's a recipe for egg? In here we have Ollama generating. We have Ollama as the interface for the Mistral 7B model, and it's giving us a recipe for eggs. There's a handy command. I'm going to say set debug. Oops. I think it's debug. Oh man, I always forget commands live. Okay, now we're going to get into the fun part of live coding. Set verbose. That's what we want. So a handy command with Ollama is set verbose. I set it. It reruns the prompt, and then we should get. We did not get it. All right, let's try one more time. And the screen is cut off. Let me pull it up. Make it bigger. All right. Again, we get pretty speedily. We get a recipe for eggs, and we should get this at the end. So because this model is running locally, it's running on my desktop. When you're going to start getting into fine-tuning and things like that on your desktop or locally, the first thing that's going to matter to you, what's going to be quite important, is just how big of a model that you can load into memory and run. Different models takes different sizes of memory. I happen to have 24 gigabytes of VRAM in my particular desktop, which is the maximum that you get for a consumer card. my RTX 90 was around $2,000. It was not cheap. It was more than half the cost of the entire computer. But you need that memory to be able to fit models into, to be able to run models quickly. If you're just doing inference, there's now a lot of tricks people use that have already been built in, so you can run large models and they sort of compute a little bit of the weights at the time, but the performance degrades a whole bunch. And what's challenging though, if you're going to do fine tuning, you not only need all the memory for inference, but you also need all the memory that's needed for gradient, for capturing the gradient weights and doing a bunch of other things as well, which we'll get into a second. But with Ollama, the reason I like it, which is quite nice, is you can quickly see what your performance is for your prompts and get a sense of whether this is fast enough for you or not, and make a decision there. Now, as you've seen, this isn't a Shakespearean JSON recipe. So the question is, what can we do? I have to always remember how to exit. Okay. So the question is, what can we do now to make our model look more Shakespearean and more JSON-y? Well, the first thing we can do, which is quite easy and actually is a great first step, is Ollama presents what's called a model interface. So let me see if I can remember the command here. Ollama show Mistral 7B. Okay. So behind Ollama is when you're running one of these models, it has what looks like a very Docker style model file. So what it does is it says from a particular model, in this case a model that it grabbed, here's the template, here's the parameter, here's the stop token for instructions. If we do another one, let's try Llama 2. Now you see we get a different one. This is the model file that's available for Llama 7B. And then I think the most interesting one to me is Gemma. Gemma, you see, has another sort of model file. This is really cool, actually, because what we can do with Ollama is we can do a very Docker-like example. Let me show you the documentation real quick. This is the Ollama documentation on GitHub. I don't know how to turn dark mode off, but this is the documentation from Ollama itself that shows you the model file spec and how it can be used. I won't read this all here, but the cool thing is you can extend existing model files. So that's what I've done back in my Gen AI guidebook. I've taken an existing model file. Let's find it. Here it is. I've taken an existing model file, and I say from Gemma B instruct quantized the 8-bit version. I want you to be a system bot, so be extra flowery in your language, output all your recipes in JSON. I have injected a system, what's called a system prompt or system instruction, that's quote unquote hidden, that's telling the bot to be different. And what's great with Ollama is I can then run that. So I can say Ollama create, and then I could I need to create, Ollama create Shakespeare Gemma, and then I give it the model file, and I tell it this is the recipes. I've already done that, so I won't run that command again. But now I can just go to Ollama, and I can say run this model. And so I'm going to wait a second for it to load the model. And I'm going to say, what is a recipe for eggs? And immediately you see that the output is a lot different. It's not the greatest. It's still very modern English, but it's different than it would have been before. So if I run the regular Gemma, oh, and so now it changed a little bit. You can see that when I click exit, it changed the output. But you can already get a sense that the default behavior is different. What we did here, though, is not actually fine-tuning. What we did is prompt tuning. Or it's actually not even prompt tuning. It's just pre-prompting the model with system instructions. So for folks who have used any of the chat models, you've probably already naturally done this, but you start telling the model to act differently, and that's the easiest way to get it to act differently. So in this case, Ollama makes it pretty easy for us to create model files that automatically inject prompts, so we don't have to write them in every single time. This is actually a really cool feature because it means that I can have a bunch of different model files that are very lightweight. They're just literally small text files of 3 lines. And I can have one that's a Shakespeare bot. I can have one that's a JSON bot. I can have one that's the expert in modern history. And now I can just use these model files for all the different tasks and purposes that I have. And I don't have to fine tune each model through an arduous process to have a library of fine tuned models. Now the downside is, as you saw, one is that you can only get so far with prompting with system instructions. You're not actually changing the model weights under the hood. So you can only really tweak the model lightly, and the model tends to forget over many turns what its system instruction could be. I haven't double checked with Ollama whether it injects a system prompt with every single request, but that's a common strategy that happens in other systems, that the system instructions get injected in silently every single time. The other downside though of system instructions is that they take up compute each time you run them, and they take up portions of the context window. So they're not ideal, because if you have a very long system instruction, you won't be able to fit maybe that and all of your normal instructions in memory at the same time. So it's a great easy trick and first step, but it's not actually fine tuning, and it comes with a couple of downsides. So with that, we've covered now tuning in the API, and we covered pre-prompting or system instructions in Ollama. What I'm going to talk about last is local fine-tuning. So this is running all of the fine-tuning on a model that's totally on your computer, with a setup that's also totally on your computer. All right. So to do local fine-tuning, there is yet another notebook in GitHub, which is aptly labeled Finetune. I will throw that into the chat on YouTube as well. And so this is the portion of the book club where I'm going to tell you where things are more challenging. So the Gen AI ecosystem is getting more and more built out with lots of great tools for people to use, both deployed tools like AI Studio, but also local tools. But it's still not always as easy as things would like to be. We'll talk about the complexity that's inherent to the problem, but before that, I'll get to just the local compute issues. As I've alluded to before, supervised fine-tuning, especially on big models, takes a ton of compute, like a lot of compute. And so I personally just have a single GPU desktop with a 4090, again, which was the most expensive GPU I was willing to buy myself. But people that are serious about this, they tend to buy systems like TinyBox from George Hotz. For those who don't know, George Hotz is this very, very prolific computer scientist / hacker that has he was the first person to unlock the very first iPhone. He did a bunch of interesting stuff on PlayStation 4s. Now he's really into self-driving cars, and recently much more into Gen AI. And so he is creating this thing called a TinyBox, or he has created this thing called the TinyBox. It is a $15,000 to $25,000 PC. Let me show you the specs. Okay, so here's the specifications. It is a $25,000 or $15,000 very large sized computer that includes six GPUs. In this case, 6 RTX 7090s, I think, is what is there. Where's the spec? With that though, you then get a lot more compute. So the idea here is this is a much more powerful desktop or server, frankly, at this point, that can be used to train models locally. It is also much more expensive though, about 10 times what I was willing to pay for GPU compute. But certainly there's people that are buying these. I think he's got a couple hundred pre-orders. And similarly, there's a fellow that I know who I met recently. He bought a bunch of Ada 6000s, NVIDIA 6000s. Let me see if I can find it. I'm forgetting the name. Oh yeah, these These 6,000, he has 6 of these in a PC himself. I guess it was quite an expensive PC build, and he's fine-tuning very, very large models. So this is all to say, what you're going to be able to do locally is going to be quite dependent on the hardware that you have. I would say at a minimum, you're going to need a 3090, which is about $1,000 graphics card at this point, or a 4090 to be able to do some of this stuff locally. You're going to soon see that I'm running into issues where my 4090 is not enough to do what I wanted to do. So what I wanted to do, if we could talk about that, is I wanted to fine tune a model in Hugging Face. I then wanted to export it to what's called GGUF format. GGUF is now the sort of standard, how do I word this? Like a compiled model that can be used in a bunch of different model interfaces, such as Ollama, because I wanted to distill a Shakespearean bot, convert it into GGUF format, and run it in Ollama. And I'm not able to do that. But I am able to do some level of fine tuning, and we'll talk about what I'm able to do and where I get stuck. So here's my Hugging Face token that I'm immediately going to burn after doing this live stream because I just exposed it on the internet. But you have a Hugging Face token. This lets you grab models from a Hugging Face. I get the Mistral AI 7B instruct. The first thing I do is I just load my model into memory. Even with 7 billion tokens or 7 billion parameters being a relatively small model, the size of the tensors that you're loaded in memory determine how much memory you're going to use. So if somebody wants me to talk about the details of quantization, I will, but I'll just cover it super quickly right now. Basically, when you have floats in memory, there's the number of bytes you can have to represent that float. And if you use less bytes, you use less memory, the compute becomes a little bit less precise. But you can fit more numbers into more floats into memory. In this case, I'm deciding I use what's called 4-bit quantization. I don't want to load this in as 8-bit, so I can fit this model into memory more readily. Once I have that model into memory, I go ahead and just prompt it. We get a very standard output for eggs, which you can see here. Now the question is, I want to fine tune it. So I grab the data set of Gemma responses, which is the one that I want. I just look at the training examples like we've looked at many times now, and we've seen for AI Studio and now here as well. This is the supervised fine-tuning training example. And then I go ahead and do a couple things. I need to format this into the format that Gemma is expecting with the control tokens and everything like that. So I'll define a formatting function. Here's what my supervised fine-tuning example looks like now once it's formatted. I have to pick a LoRa configuration. So I won't talk about LoRa here. We've talked about LoRa before in the supervised fine-tuning guide, but I tell it which specific portions of the model I want to then add the LoRa weights onto as well. I set a bunch of parameters. Some of these are familiar that you've seen from AI Studio. Some of these are newer, which is the optimizer, which we didn't have access to on AI Studio. I tell the model to train. And once I get it, once it's trained, which takes about 30 minutes when I ran this many epochs, I now get a fine-tuned example locally. And so what's cool is now I have a model that runs locally that is fine-tuned in the manner that I want it to be fine-tuned. Where I get stuck, if we go to that, is that to convert this to GGUF format, I can't do it with a 4-bit model. There actually are, I'd have to convert it, I'd have to be able to do this with 16 bits if I remember correctly, which didn't fit in my 2040 with fine-tuning. The 16 bits fits for inference, but it didn't fit for fine-tuning. But I would need to do that, and then I would need to export the 16-bit floats to a format, run this GGUF conversion script, and then that would get me to Ollama. So if I show you what that looks like with NVIDIA SMI, when I was running this locally, which I won't do right now, but previously I took a screenshot, just running the supervised fine-tuning environment ended up taking around 23.2 gigs of VRAM, and that is almost all of the available RAM that I had on my 4090. So a single 4090 was not sufficient to train this particular model, which is a little bit of a bummer. So I mean, there's a couple things I could do. One is I could just wait for larger GPUs to come out that are hopefully cheaper, like the 5090 or whatever when it comes out, and hope it has more memory. Or I could go buy a tiny box. But I am not the type of person that wants to spend $25,000 on a PC right now. So for me, this is the end of my fine-tuning run. Another common strategy which people talk about or people use quite often is you go to one of the cloud providers. There are many of them now, but you go to like an AWS or GCP, or I'm forgetting now the smaller companies. I think it's like Lambda Labs, but these companies have large data centers that are dedicated for fine tuning. So like with a bunch of H100 enabled virtual machines, and you would rent these computers from them on the cloud. So I would go take my notebooks and everything. I would upload them to one of these cloud providers that let you, again, connect up to an H100. And then I would use like an H100 cluster to do this. Currently, what I understand the pricing to be is about like $3 to $4 an hour to rent one of these clusters. So for a task like this on an H100, probably it shouldn't take that long. I think it would take maybe 15 to 20 minutes. So you should be able to get a fine-tuned model then for about maybe like for less than $10, 10 US dollars, if you really need one. So that's the other path if you don't want to buy your own dedicated compute. All right, so this actually turned out to be quite an efficient book club. I think one of the better ones that I've done. So I'm still updating the guide a little bit, but in here you'll have references to all the stuff that that I was talking about, and references for how to export and fine-tune models locally. As always, I have references for Ollama and everything in here as well as OpenAI and Gemini AI tuning. So if you see anything that you want, you always know how to reach out to me through the mailing list or on LinkedIn or YouTube or wherever you find this. I hope that was an instructive guide on how to fine-tune models in various different ways, hands-on as well, not just theoretically. I'll pause here for any questions before I jump off. As always, I have to wait about 15 seconds. While I'm waiting, I will say I'm not quite sure what the next topic I want to talk about or write about will be. The ideas that I had in my head were multimodal models, though with a caveat, it's going to be hard to get into depth with those for a lot of reasons, but we can do, let's say, like a 30,000 foot view of multimodal. We could also do tokenizers. Andre Karpathy has a full guide on tokenizers now, and as you know, I really like his content, and we could do a shortened guide on that. But those are the two that I had off the top of my head. There's a couple others you're gonna see, which I won't reveal right now. That will come out pretty soon, which I'll be excited to talk about. But for now, those are the two that I'll each choose between: tokenizers and multimodal. So let me know which one of the two is more interesting to you whenever you watch this. Nitesh, all votes multimodal. Okay. So the either guy that shows up, we'll cover multimodal next at a 30,000 foot level. Just a spoiler alert, it is very challenging to build multimodal models to run locally. Actually, probably, I don't want to say impossible because it's obviously possible, but like not very easy. So we'll talk a little bit about that. And then I don't think there are many open source multimodal models at the moment that are super notable. I think there's a Lava model and a couple of others, but let me compile what we have on multimodal. It is frankly, an area that's moving quite quickly. Models that have image understanding and image capabilities and whatnot. It's super, super cool. So, all right, that's what we'll talk about next. With that, it seems like there's no other questions that are open. Always a pleasure to do this book club with you folks, and I will see you next time.